Welcome to today's deep dive. In precision mechanical engineering, the biggest threat to a system isn't like a giant hammer or some massive visible
Oh,
flaw.
definitely not.
It's literally a fraction of a degree of heat, or an alignment error so small that you would need a microscope to even see it. And looking through the research you sent us on advanced precision manufacturing, it just completely shatters that traditional image of, you know, brute force production.
Right, because at this level, the vocabulary we're using is basically just applied physics. I mean, it's all about controlling these microscopic variables.
Exactly. So our mission today is to explore how this invisible perfection is actually achieved. And more importantly, how these concepts physically impact system performance in the real world. So let's just jump right into how you shape raw materials without losing perfect alignment.
Yeah, the foundation there is something called five-axis simultaneous machining.
Right, which sounds intense.
It is. I mean, instead of moving a cutting tool along just an X, Y, and Z axis, you actually have five separate coordinate axes working together simultaneously. So the machine can tilt and rotate both the cutting tool and the part at the exact same time. It gives you incredibly complex spatial profiling in just a single setup.
It kind of sounds like sculpting a statue in zero gravity, right? Like you never have to actually put it down and pick it back up at a slightly wrong angle.
That's exactly it. And physically, avoiding that whole putting it down and picking it back up routine
Yeah.
is how engineers ensure perfect perpendicularity for things like pinholes.
Oh, because the moment you unclamp it, you mess up the alignment.
Precisely. Unclamping and reclamping introduces a tiny margin of error, but a single setup just eliminates that entirely.
Okay, but even with that zero gravity mobility, if you have to take the part out of the mill to, say, move it to a completely different machine just to turn it, haven't you just ruined it?
You have, which is why manufacturers rely heavily on multitasking machines.
Ah, okay.
Yeah, they basically combine turning and milling into one unified system. So again, minimizing handling reduces clamping errors, which is absolutely vital for maintaining perfect concentricity.
Meaning the center point is just totally flawless.
Right. If you're processing a rotating component, like a sun gear shaft in a transmission, perfect concentricity ensures it doesn't just vibrate itself to pieces at high speeds.
That makes perfect sense for a solid block of metal. But wait, what about incredibly delicate, thin-walled parts? Like, achieving perfect geometry on a fragile component like a flex spline seems like a totally different challenge.
Oh, it is.
Because wouldn't the violent, heavy cutting required to shape metal just instantly destroy something that fragile?
You would think so, yeah. It sounds really counterintuitive, but the solution to cutting fragile parts is actually moving much, much faster.
It really faster.
Yeah, they use a high-speed spindle. It operates at these incredibly high RPMs, but with very, very low inertia.
Oh, get it. Meaning there isn't a massive amount of heavy, lingering momentum behind the blade driving it forcefully into the part.
Exactly. Because of that low inertia, they can use micro-end mills.
Tiny cutting tools.
Right. Ultra precise. So instead of taking aggressive, forceful gouges out of the metal, the high speed allows the tool to make thousands of tiny, low-stress cuts.
Wow.
It completely avoids the stress concentration that would otherwise warp or just crush a thin-walled component like a flex spline.
Okay, so doing this perfectly once is impressive, but doing it thousands of times has to introduce a whole new set of physical problems. Like,
Yeah.
how do we produce these at scale without the machines sitting idle?
Well, to tackle efficiency, facilities use what's called a pallet pool system.
A pallet pool.
Yeah, it's essentially an automated carousel for workpiece exchange. So while the spindle is inside cutting one part, robotic arms outside the cutting zone are simultaneously unloading finished pieces and locking new raw materials into place.
That is incredibly efficient. It just drastically cuts down non-machining time.
Exactly, massively increasing the machine's utilization for high-volume production.
But hang on, if a machine is running continuously at high RPMs for a massive volume of parts, you're generating constant friction, right?
Oh, definitely. Tons of it.
And friction creates heat. Physics tells us metal expands when it gets hot, so doesn't the machine itself start to slightly change shape?
It absolutely does.
Yeah.
The friction causes what engineers call thermal drift.
Thermal drift, okay.
Yeah, the metal of the machine and the workpiece literally expands. And if you're boring a high-precision hole, even a microscopic expansion ruins the tolerance completely.
So how on earth do you maintain perfect tolerances if the machine is physically changing shape while it works?
That is where adaptive control comes in. It acts like the machine's brain.
Oh, fascinating.
Yeah, sensors track the microscopic thermal expansion of the metal and monitor the real-time resistance on the spindle. That data is fed back into the system instantly.
So the machine actually optimizes its own cutting parameters on the fly, like
Yeah.
feed rate and speed.
Exactly. It auto-corrects to compensate for the heat.
It acts like a smart thermostat for the cutting blade. If sensors detect the metal expanding by a micron, the system just automatically backs the blade off by a micron to maintain the exact same cut.
Precisely. It creates this highly responsive, auto-correcting manufacturing loop.
That is just wild. We've moved from basically carving complex geometries in midair to high-speed microcutting, all the way to machines that autocorrect their own temperatures.
It really is a completely different world of manufacturing.
It really leaves you wondering, if machines can now adaptively sense and correct their own microscopic thermal drift in real time, are we approaching a future where post-production quality control becomes entirely obsolete?
That's a great question.
I mean, why check for errors if the machine physically refuses to make them? Something for you to think about the next time you look at a perfectly machined piece of metal. Thanks for joining us on this deep dive.